try to develop the quadratic formula today, shall we? And before we do so, let's look at an idea such as x minus 4, the quantity squared. And if we were to multiply this expression out, of course we know that this is equal to, Tim?
X squared
X squared
minus 8x
minus 8x
plus 16.
plus 16. Everyone agrees with that? All right. Now, suppose I then were to write simply x squared minus 8x plus what number then is going to give us x minus 4, the quantity squared? And we're now thinking of some number which we can put in here, which is then going to, what we say, complete the square. And what number would we like to put in there, Malcolm? 16. Is the number 16, certainly. Suppose we then were to look at another example, such as x squared plus 6x plus what number is then going to be equal to, say, x plus 3, the quantity squared. And what number would we like to put in here, Doug?
9.
Is the number 9. Everyone agrees with that? All right. How about x squared plus, let me call it ax plus some number is going to be equal to x plus, what would I like to write over here? But, what? A over 2, the quantity squared. Is that right? Now, what number would we like to have in here, which is then going to give us this completed square? Brenda?
A squared over 4.
A squared over 4. Is that right? Now, in each case, let's look, for example, at x squared minus 8x plus 16. Where did this number 16 come from? Can you generalize this? Is there some way in which one can determine this number which we are adding in order to complete that square? And can anyone see any generalization here, Tim?
Multiply the last number on the right.
All right, this number, we're looking at this number 16. You're concerned with this number 8. Is that right? And does anyone see any pattern that is emerging here, Brenda?
You divide it by 2 and then square the number.
Take 1/2 of this number, which is 4, and then square it. Take 1/2 of this number, which is 3, and then square it. Take 1/2 of this number, is that right, which is a over 2, and then square it. And indeed, that's exactly what we have here, because when you multiply this out, you then are going to have twice the product of those two terms. Is that right? Well, let's look then at, say, x squared plus b over ax plus some number is then going to be equal to x plus, what would I like to write over here, but b over, what, 2a, the quantity squared. Now, what number do you think you'd like to add here in order to complete the square? And does anyone see that, Doug?
B squared over 4a squared.
B squared over 4a squared. Does everyone agree with that? And in fact, this whole idea here is called completing the square, all right? Completing the square. And we need this idea in order to be able to develop the quadratic formula, and that's the reason why I went into this in some detail. Let's then look at the general case of a quadratic equation. Ax squared plus bx plus c is equal to 0. Now, the fact that it is a quadratic equation, immediately what must we say about the number a? A cannot be, Bill?
0.
A cannot be equal to the number 0. In fact, if a were equal to 0, immediately you are down to a linear equation. Is that right? So we're now dealing with a quadratic equation. Well, rather than go through a specific example, we probably could go through 5 or 6 or 8 specific examples and then try to make a generalization. Let's see if we can't jump right to the generalization. All right? And perhaps the first thing that one would like to do is to divide through both sides of this equation by the number a. And since a cannot be 0, certainly we can do so. And we have plus c over a then is equal to 0. Let's subtract this number from both sides, in which we have b over ax is then equal to the opposite of c over a. Now notice right here on the left-hand side, we have an expression x squared plus b over ax plus. Now let's complete that square. And in fact, we've already just done this example. And Peter, what number would you like to add here in order to make this into a perfect square?
C squared over a squared.
Well, let's see now. We're dealing with this number b over a. Don?
B squared over 4a squared.
B squared, okay, all over a 4a squared. And now, of course, if we add this number to the left side of this equation, our theorem tells us that indeed we must add the same number to the right-hand side of our equation. Is that right? And the whole purpose of doing this is to be able to look at this left-hand side and write it as what? X plus, now what number would I like to write here, but what is that name, Don?
B over 2A.
B over 2A, the entire expression squared, is that right, is then equal to, let's rewrite this a little bit, and we have there B squared over 4A squared minus, now let's get this all over the same denominator, which is, here we have a number A and a 4A squared, and the least common denominator there is what? That's 4A squared, so then in the numerator we have what? There is what? 4AC, is that right? Now, in fact, perhaps we could have done this in the previous step, but now let's get this all over the one denominator of 4A squared, and in the numerator, notice we have B squared minus 4AC. Now, here we have a pattern y squared equals some number d, call it. And we've already handled situations like this. If we have y squared is equal to d, and from the theorem that we developed in our last lesson, therefore we have x plus b over 2a is equal to, now the fact that this is a square tells us that we have what? We have two possibilities here, one of which is the positive square root of b squared minus 4ac all over, now the square root of 4a squared is 2a, or, remember our theorem tells us that we have a, if you remember yesterday's theorem, it was d is equal to e, or d is equal to the opposite of e, is that right? In which we have here d squared is equal to e squared, d then is equal to e, or d, which is x plus b over 2a, is equal to, and how may we write that, but, Bill?
The opposite of the square root of b squared minus 4a over 2a.
Okay, 4ac all over 2a. Now, let's then, with this word or, combine these two sentences, these compound sentences, into one if we can. At the same time, let's subtract this number from both sides, all right? Which we have the opposite of b all over 2a, and let's write this as plus or minus the square root of b squared minus 4ac all over 2a. Is that right? In which this plus or minus business is to put into one statement, into one sentence, this compound sentence with the word or, all right? And notice here we have the same denominator, therefore we have x then is equal to what? The opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And this, in fact, is what we mean by the what? This is called the quadratic formula, okay? And it's a statement that certainly every person who goes through an Algebra 1 and an Algebra 2 course certainly knows. Let's write this as a solution set, if we may. Our original equation is ax squared plus bx plus c is equal to 0, where our domain is over what set of numbers? Our domain, Bill, is over the set of real numbers. With a set of real numbers. And so what we are interested in is a solution set over the set of real numbers. And so one number which will make this sentence true is the opposite of b plus the square root of b squared minus 4ac all over 2a. And the other element is what? The opposite of b, and what is it but minus the square root of b squared minus 4ac all over 2a. And indeed, inside our set bracket, I think we had better specify when these numbers are going to end up to be real numbers. And when will these roots be real numbers in order to see if indeed we have any roots here. Brenda?
When b squared is greater than 4ac.
All right, let's write that when b squared minus 4ac, when the entire expression is what? Greater than or equal to 0, will then guarantee us some real roots. Okay? And this then would be the solution set of our general formula of the quadratic as we have right here. Well, let's look at a specific example of this in which, suppose I were to make up some problem such as 2x squared minus 3x is equal to 4. Now notice here, it's not set up in quite the pattern that we would like it to be. So you say to yourself, well, if I were to subtract 4 from both sides and set it equal to 0, now I think perhaps it's worthwhile to look at any quadratic equation. The only method that you have at your disposal thus far before this formula was to factor it. Is that right? And so you look at this and you ask yourself, well, can I factor it? And if you spend perhaps 5 seconds or so just thinking about it, in some cases it is possible to factor these, and immediately you are where you want to go. but I think perhaps if you look at this for more than 5 seconds, you would say to yourself, I don't think I can factor it. Well, if you cannot factor a sentence, one of these equations, then indeed what do you think you'd like to do but to go directly to the what? To the quadratic formula. And so perhaps it's worthwhile to indicate what the numbers a, b, and c are equal to. In this case, a is equal to 2, b is equal to, careful now, it's -3, and c is equal to -4, okay? And now let's then rewrite our formula. X then is equal to the opposite of b, plus or minus the square root of what? B squared minus 4ac all over 2a, which is then going to be equal to, now let's make our substitution. The opposite of -3 is 3, plus or minus the square root of -3 squared is 9 minus 4 times a, which is 2 times c, which is -4. Is that right? And let's see. I don't think I have that parentheses there. All over 2 times 2. Okay. And then this is equal to 3 plus or minus the square root of, there is 9, a -4 times 2 times a negative, what number did I want to have in here, but negative, what? 4, is that right? Is equal to what number? -4 times 2 times a -4 is
32.
a positive 32, is that right? Plus 32 all over 4, which is then going to be 3 plus or minus the square root of what? 41 all over the number 4. And in fact, there then are our two roots. If we were to write this as a solution set, we have 3 plus the square root of 41 all over 4, and 3 minus the square root of 41 all over 4. And certainly these are real numbers. And in fact, what kind of numbers are they? They are, what? They are irrational real numbers. Let me give you your homework assignment for next time. This will be